Welcome to the presentation of the paper Real-Time Intelligent Autonomous Intersection Management Using Reinforcement Learning, and I'm Udish Kunratne, one of the authors of the paper. So let's look at a common scenario that we encounter every day, that is waiting at intersection. So the traffic congestion at intersection is more critical for overall performance of the transportation network, and finding a better way to handle intersection is a critical way to improve the traffic congestion at overall transportation system. So let's look at why we have to sort of wait a large amount of time in this intersection. So one is, whenever we have red signal, we have to come to a complete stop, and then we have to accelerate from the beginning, and which will disrupt the traffic flow. And the other thing is, whenever we are switching between traffic signals, then we have a vacant time that where no vehicle is using the intersection square. And also, whenever sometimes when we wait at red signals, but there are no actual vehicles in other road segments that are crossing, but simply since the traffic signal is red, we have to wait either way. So the next question is, can we do better? That means avoid this type of challenge drawbacks and improve the intersection throughput. So what one possible way is to allow all the vehicles to collaborate at the intersection so that they can cross the intersection without using traffic signal. So this is actually a very challenging thing to achieve with human drivers, because we set of humans cannot maybe figure out collaboratively who to give way. That will actually result in crashes, and they have sort of a lot of other safety issues in that type of approach. But with the emergence of these autonomous vehicles and intelligent or smart traffic infrastructure, we might be able to provide a solution for this type of approach. Intersection management, which is a way to replace traditional traffic signal control. So this was proposed by Dresner, and in this approach, vehicles will coordinate their arrival time and speed so that vehicles can traverse the intersection without collision, with the help of intersection manager or a intersection controller. So in this case, intersection controller will get requests from each vehicle and regarding a time, and intersection manager will, if that time slot is available, it will inform back to vehicle itself to achieve the coordination. And in this approach, vehicles will have first come first serve order. That means the vehicles will travel the same order as they will drive to the vicinity of intersection. Now let's look at few ways we can improve this behavior. So some improvements to AIM is, first, rather than having this first come first serve basis, we can improve this by allowing to optimize this traversing order. For example, we can leverage benefits from platooning behavior to improve the throughput of the AIM solution. Now the second way is, whenever vehicle crossing the intersection, if the vehicle crosses the intersection at a higher speed, then the amount of time that it takes to cross the intersection will be reduced. That means we can allow that save time for another vehicle, or we can improve the stop and go nature. Now the next part is about how to compute a solution, come up with a computation solution for this type of paradigm. Now the main challenge is the computational time in this type of application, because vehicles are arriving stochastically towards the intersection, and we have to compute schedules and trajectories and everything at real time with low computational complexity. For example, if the intersection controller takes a lot of time for respond to the messages that are coming from the vehicles, then actually the vehicle's position may have changed, and the given schedule times may not be feasible anymore, which may lead to vehicle crashes. As well as, whenever some instruction came from the intersection controller, if the autonomous vehicle's computation time for trajectories is high, then again it will lead to infeasible trajectories, which will lead to some collisions between vehicles. So that is the major challenge existing AIM solution when we are applying it real time. So we propose a multi-agent solution which consists of two types of agents to reduce the computational complexity and provide more efficient computation component. So the first type of agent is the set of one coordinating agent virtually located at the center of the intersection, where this responsibility of this coordinating agent is to optimize the traversing order, where coordinating agent will instruct all the vehicles that are in the vicinity of intersections arrival time to reach the intersection starting point. And then we model the vehicles as set of distributed RL agents which can plan trajectory for a given schedule time. So in that way, we have reduced the computational complexity by dividing into two optimization problems. And let's look at about behavior about coordinating agent and RL agent detail in the next few slides. Okay, now let's look at the behavior of coordinating agent. So the coordinating agent uses a polling-based algorithm, and the objective of this coordinating agent is to find an optimized traversing order for all the vehicles that are in the vicinity of intersection. And based on that optimized traversing order, each vehicle has to be assigned with a arrival time to reach the intersection starting point. Now, in this type of polling system, we model the vehicles as a set of customers in a set of queues, and a queue is related to each lane, and the intersection controller is modeled as a server, and the common resource these vehicles are trying to access is the intersection crossing square. Now, let's look at how this algorithm works. First, the server will pick a customer from each queue. That means a vehicle from one lane, and the service time is defined as the amount of time that it takes a vehicle to cross the intersection square. And whenever we are selecting vehicles among different queues, that means we have first select a vehicle from one queue, and if you are switching to another queue, then we have to spend this switching time to guarantee the additional safety to avoid collisions. And you can see if we have more switching times, then the amount of time that it takes to serve all the customers will be increasing. So the objective should be to reduce the amount of switching time between queues, and then we can actually achieve this platooning time by like behavior. Even though the previously described polling system is event triggered, that means that it can handle vehicles that are coming to the intersection stochastically with a low computational time. This type of formulation is only capable of handling intersections that are having one single lane at every road segment, as well as vehicles that are going straight through the intersection without turning right or turning left. So in this work, we modified this type of polling system to handle much more complex intersections with having multiple lanes as well as multiple turning directions. The main issue when we have multiple lanes and multiple turning directions is the switching time between lanes is different. So rather than using fixed switching time and a fixed service time, we propose a queue dependent matrix which will have information about amount of time that we have to wait if we are switching between different lanes. In this way, when we are selecting a vehicle from one lane, and then we can take the impact from all the other lanes and take the earliest safest time using a maximization operation. And this maximization operation is linear with the number of lanes in the intersection, and since the number of lanes in an intersection does not increase exponentially, this modified polling system is also computationally efficient. Further, this system allows more than one vehicle to exist in the intersection square in a non-conflicting manner, thus improve the throughput. Once the polling-based coordinating agent assigns arrival time for every vehicle to reach the intersection starting point, the objective of reinforcement learning agent is to control the vehicle trajectory to reach the intersection exactly at the scheduled time. So there are actually two objectives here. The first objective is to reach the intersection exactly at the scheduled time. So we have to compute a trajectory for that, and while doing so, we have to ensure we reach the intersection at the maximum possible speed. Then actually we can minimize the amount of time that it takes to cross the intersection. So naive way to achieve this type of behavior is waiting very large distance at the intersection and maybe accelerating at the last point. However, that type of behavior block all the traffic that are following that vehicle. So while achieving this objective one, we also have to stay closer to the intersection as much as possible to allow other vehicles to enter the road segments. And while we are achieving this objective one, the objective two is we call as cruise control task, where we have to be aware of the vehicle that we are following and we need to avoid crashing with the front vehicle. So the RL agent needs to achieve both objectives. However, achieving both objectives at the same time is not a trivial task, because the trajectory control task is sort of a long-term planning task where we get to the intersection at the very end of our objective. However, cruise control task or avoiding crashing with the front vehicle is a short-term behavior, because we have to act whenever the front vehicle is close to us in a short time period. Typically, the reinforcement learning algorithms are designed to learn either a task as a short-term task or long-term task only. For example, Q-learning uses a parameter named discount factor, which can be set either as a short-term task or a long-term task, but not at the same time. Naive way to achieve this objective is maybe to have two different agents which control trajectory and the cruise control task, but that type of naive approach may not be able to capture the interrelationship between these two tasks. We propose a new RL algorithm named multi-discount Q-learning to achieve both long-term and short-term tasks by preserving their temporal nature. And in this approach, we consider the output from two tasks as a vector and use this vector to come up with a function named reward dependent discount factor to replace the traditional discount factor. And this function is able to adaptively change the temporal nature of the RL agent learning process to handle both tasks simultaneously. And we have compared this with the naive Q-learning algorithm as well as other baselines, which shows our multi-discount Q-learning achieves superior results, and these results are available in our paper.
So let's look at some experimental results. In this experimental setup, we have four-legged intersection, and vehicles are generated as a Poisson distribution, and the average travel time are computed. So we have four baselines: the DTS, dynamic traffic signal; FCFS, AIM, so that is first come first serve AIM, that is a traditional AIM technique, and the next three uses the our polling based coordinating agent, and the HAIM replaces the RL agent behavior with a heuristic to learn the trajectory, and the LP means the linear programming based approach, which replaces the RL agent part with when computing the trajectory. So the CMQ-AIM our proposed approach, which stands for coordinated multi-discount Q-learning with AIM. As you can see, all AIM methods outperform dynamic traffic signal, which emphasizes the benefit of AIM. And compared to traditional AIM technique, the other three baselines perform well, especially within mid and high level traffic condition, because the first come first serve AIM does not optimize the traversing order. And this optimizing traversing order is the sort of major part for reducing the travel time. Because of that, actually last three baseline have similar travel times, but however RL agent was able to perform well in that case, and we will look at into these three baseline more detail in the next result section. Measure the safety of this approach, where when a vehicle is assigned with a arrival time, the vehicle should reach the intersection starting point exactly at that time. However, failing to do so will have very severe safety issues. Heuristic approach, and as well as in the linear programming approach, you can see we have some number of violations in all these traffic levels. However, in RL based approach in CMQ AIM, we don't have such violations. This is because the RL agent directly learns about the traffic dynamics using interact with the simulation environment. However, LPOH AIM techniques sort of uses their pre-built mathematical model to compute this trajectory. So you can see the RL agent can actually learn directly from simulation dynamics and control the trajectory better than the other methods. And this is emphasizing that the using RL and the polling based system is very well suited for this type of AIM, and it allows AIM to be deployed in the real time road network.